So the next speaker is Narain, and he's going to tell us about heterotic strings.
Right. First of all, let me just say a few words, since this is Bal Fest, a few words about my experiences with Bal. So, I joined Syracuse in '76. That year, Bal was on a sabbatical to India. In fact, the whole year. But then, I met him after that, after 1 year. And then there were these brilliant students of Bal who joined. First was Parameshwaran, then Rajiv, then Fidele. And, it was and the thing that I remember most was, even though I was not Bal's student, they used to have discussions almost after lunch, almost every day. And he would also knock my door, ask me also to join. And it was really a great learning experience for me, just to sit there and listen to these brilliant discussions, So I really learned a lot from those meetings, And of course, I should also mention so many evenings I spent at Bal's house and had South Indian food with Indra and Okay. So I'll try to be very, very brief because I think we are over time. And So the topic that I'm talking about is string theory, which is, I think, a bit outside this meeting. So what I'll be talking about is heterotic strings compactified on T3 mod Z2, and compare it with the Nikulin, the M theory compactified on K3, where you have a Nikulin involution on K3. Okay, Z2. I'll be only considering Z2 involutions. Okay. So first of all, let me see. This work was done in collaboration with Bobby, Gerardo Aldazabal, Ana Maria Font, and Aida Zadeh. And this appeared in the JHEP. It's a long paper, but this talk will be very, very brief with no mathematical details, just basically qualitatively describing what was happening. Okay. So M theory compactified on K3, this is a kind of known fact. The M theory compactified on K3 gives a 7-dimensional theory with 16 supercharges. And the rank of the gauge group is 19 plus 3. And this comes from the 3-form fields expanded in terms of the 19 anti-self-dual and 3-self-dual 2 forms, on K3. Membranes wrapped on the 2 cycles of K3 are charged under these gauge fields. And these charges span a lattice gamma 19,3, which is even and self-dual. Okay. With the Lorentz signature 19,3. The heterotic dual of this theory is simply a T3 compactification of the 10-dimensional heterotic string, and combining it with the, so this is obtained by compactifying on T3 and combining with E8 plus cross E8, or one gets a charge lattice of 19,3, which is even and self-dual with Lorentz signature 19,3. So this is the way the identification works on the 2 sides. Okay. So now we're going to consider non-supersymmetric orbifolds of heterotic string T3 obtained by reflection on 2 of the 3 right-moving directions. So remember, in heterotic string, you have the left-moving sector and the right-moving sector. Left-moving sector is a bosonic string, which is a critical dimension of that is 26 dimension, and the right-moving string is a fermionic string, whose critical dimension is 10. This is combining this. So from this, the fact that there's a 26 on the left and 10 in the right, there are 16 directions which are purely left-moving. Okay, so it's a kind of asymmetric. I mean, you have string theory. Okay, so now what we're doing is that we want to consider a heterotic string and consider a Z2 orbifold, non-supersymmetric orbifold of heterotic string obtained by reflecting 2 of the 3 right-moving directions. Right-moving, these are the fermionic directions, fermionic string directions, and S of the 19 left-moving directions. So these are the Z2 asymmetric orbifold. Okay. Actually, we'll see later on that Z2 is always automatically promoted to Z4. So, but we would expect these models to be dual to M theory on K3, modeled by Z2 involutions, that acts on the membrane charge lattice. Okay. This membrane charge lattice, as we mentioned, is gamma 19,3. And this Z2 involution that I'm talking about in the heterotic string is exactly acting on the gamma 19,3, right? So, so what are these Nikulin involutions? These are the involutions on K3 that leaves a Kähler form invariant, but gives a sign to the holomorphic 2 forms. Okay. And this has been classified by Nikulin in 1980 in terms of the sublattice I of gamma 19,3, which is invariant under the involution. Okay. So the sublattice I, what I mean by that is a sublattice of 19,3, which is invariant under this Nikulin involution. So this classification is given by 3 numbers, R, A, and delta, where R is the rank, is a dimension of I. Okay, R is a dimension of I, which has signature R minus 1, 1. Okay. Why is it R minus 1, 1? Because as we said, we are looking at, on the fermionics side, we have just 2 reflections. Okay, so that leaves still 1 direction left over, and the remaining R minus 1 comes from the anti-self-dual forms. And the number A is defined by I star over I. Okay, I star being the dual lattice to I. Okay. So it is the order of this I star divided by I. So remember, because gamma 19,3 is self-dual, the invariant sublattice will be an even integral lattice. Okay, not self-dual necessarily. So it will be even an integral lattice. The dual lattice, therefore, will be, the I lattice will be contained in the invariant, in the dual lattice. I star, I is contained in I star, and this 2 to the A is simply the I star, the order of the I star over I. Okay. So that is the number A. And delta, finally delta is just 0 or 1. When delta is 1 when the I stars have integer length squares. Okay. You see, for the fact that I is integral, and you can immediately deduce that this I star, length squares of vectors and I stars are either half integer or integer. Okay. So what this condition is saying is that if it is integer, then delta is 1, otherwise delta equal to 0. Okay, that's a classification given by Nikulin. So we denote by n the sublattice of gamma 19,3, which is orthogonal to I, and therefore has dimension. How do I go to the next page? Page down. No, yeah. So this table summarizes the Nikulin's classification. So here on the horizontal axis is R. R is the same as 20 minus S. S is the number of directions one is reflecting. And A is the number that I mentioned, I star over I, order of the I star over I. And delta equal to 0 and 1 are denoted by, delta equal to 0 is a blank circle, and delta equal to 1 is the other one. So there is the black spots. So that's the classification given by Nikulin. And what our aim is to look at the heterotic string constructions and obtain all these points. Okay, that's our aim. Page down. Okay, so idea here is to so in heterotic string, as we mentioned, there is we basically reflect. We do a Z2 reflection on 2 of the right moving directions, and R minus S minus S of the S minus 2 of the left moving directions. So this is the thing. So to understand this construction, it is more instructive to look at just to look at SU2 flat connections on the T3. Okay. Because remember, heterotic string is compactified on T3, and even though the gauge group is E8 cross E8, it is better to first look at the SU2 and see how what happens, what are the different sectors that you can write down. So T3 coordinates, we just write them as x1, x2, x3, 3 Euclidean coordinates, which are of course periodic. This equation number 1 just gives the generators, xi going to xi plus 1. And in order to have a T3 over Z2, we have also a fourth generator, which identifies these points, x1, x2, x3, to minus x1, minus x2. And I'm considering here a freely acting orbifold, so I have just shifted the x3 to x3 plus half, although it's not necessary. When we discuss string theory, we don't need to really talk about the freely acting. This is just to understand in a field theoretic language. Okay, the fundamental group can be described abstractly in terms of these 4 generators, Gi and G theta. Gi are the standard generators for the torus, and they are obviously commuting with each other. Gi Gj is equal to Gj Gi for all I 1, 2, and 3. And the fact that G theta is a reflection of the x1 and x2 directions, it gives us this formula that G theta G1, G theta inverse is G1 inverse, right? And similarly for G2. Whereas G theta does not do anything to x3, it only does a shift, okay? So the fourth equation is without, I mean, the right-hand side is G3 again. And finally, G theta square is equal to G3. That again, one can see from the equation number 2. Okay. So this is the abstract relation between these generators. And now, what we want is to look at all the possible flat connections on the heterotic string, E8 cross E8, or spin 32 over Z2 gauge bundle. So these are specified by some Wilson lines. And these are for each generators, obeying these relations. Okay? So we want to map these G's into the gauge group, okay, which satisfy the same relations. Okay. So there are two types of solutions one can write. So here we are again looking at SU2 for the time being. Then once we understand SU2, we can extend it to any of these Lie algebras here. So one of them we call Higgs branch, and we can write this as, so G1 is some generator, some group element along the third direction, sigma 3. G2 is again in the same. And G theta is I sigma 2. G3 is minus 1. Okay? This is the Higgs branch solution. One can verify that this choice satisfies all those equation number 3. Okay, note that G theta in those solutions satisfy G theta to the 4 is equal to 1. So it's really a Z4. Okay, this solution can be easily generalized because anyway, you can decompose E8 cross E8 or spin 32 over Z2 in terms of SU2 to the 16. No? So we can just take 16 copies of SU2 and put this, generalize it. Now these solutions have a moduli space, which is, page up here. You see here that phi1 and phi2 are continuous parameters. So these are the moduli. Okay. And so these have a moduli space. Which are parameterized by phi1 and phi2. Hence, a low energy effective field theory will contain 2 light scalars, which will naturally form a complex scalar field. And at the origin of the moduli space, when phi1 and phi2 are equal to 0, then there is an SO2 subgroup of SU2, which commutes with the flat connections. So these are the SU2 matrices with real entries. Therefore, the 7-dimensional theory has an enhanced SO2 gauge symmetry at that point, okay, which is broken for generic values of phi1 and phi2. So that's why we call it Higgs branch. So by giving Wave to phi1 and phi2, you are breaking the gauge group. I mean, breaking the rank itself. So that's one branch. Other is a Coulomb branch solution. And these solutions can be described in the following way, right? G1 and G2 are mapped to identity. G theta is some element in the U1 subgroup generated by sigma 3, and G3 equal to J theta square. Okay. So this is a Coulomb branch. Okay. One can easily see that this doesn't break the gauge group. Okay. That's the Coulomb gauge. Okay. We can extend this to any gauge group, as we mentioned before, in terms of for the E8 cross E8, also 32. Now, one thing that one should notice, and this plays an important role here, that if you go back to the Higgs branch solution, right. No, this is not. I should go up, page up. Yeah, if you look at the Higgs branch solution, and if you set phi1 and phi2 equal to 0, and just instead of G theta being equal to I sigma 2, you rewrite it as I sigma 3, which can be done by just the group rotations, right? You arrive at, again, the Coulomb branch solution. No? So at the point phi1, the zero values of phi1 and phi2 of the Higgs branch, there is an intersection. These two branches intersect at some point. So this will be an important thing because we'll be able to make transitions from the Higgs branch to the Coulomb branch by going to that special points. And this way we'll be, in fact, able to connect all the different Nikulin points, which you don't see in the M-theory language, but in the heterotic side, these transitions will be quite easy to understand. Okay. Now returning to the asymmetric orbifold of heterotic string on T3, where now we do not necessarily restrict to the freely acting orbifolds. So I will not give any details here, just basically summarize the various points here. So first of all, what is the group action? It is on the right movers, as we said before, right movers, which means fermionic string sector. The G acts as a rotation by pi on a two-dimensional plane. Thus, G square acts as -1 on the space-time fermion, right? Because this rotation, G square is rotation by 2 pi, but on the fermions it acts as -1 space-time fermions. And therefore, really, this G is of order 4. So this is a Z4 orbifold, actually. This would not have been the case if we had rotated 2 planes, like in order to get, for example, K3 orbifolds. That would not have been the case because you're rotating 2 planes by 2 pi, so fermions come back with a plus sign. No? But this one picks up a minus sign, so it necessarily becomes Z4. Okay, in general, we may also include some shifts in the definition of G, that is, which acts on the states P carrying the lattice momentum P. I mean, of the E8 cross E8 or SO32 over Z2, spin 32 over Z2, lattice, the charge momentum P. Yeah. So it can act also, apart from this rotation, it can also have that action. Okay. More generally, when the lattice vector P belonging to 19,3 has components along both I and N directions, then G will act in the way shown in equation number 6. So Pn and Pi so P is a vector, and Pn or Pi are the components along the N directions and I directions. So I directions, again, remember, it is the invariant directions under the rotation, and N directions are the normal directions to that. So P under the action of theta, Pn Pi goes to minus Pn comma Pi, and G acts as given in equation 6. So from equation 6, if you take G square, you get equation number 7, and now you see Pn Pi is mapped to the Pn Pi. So this product Fpn times F minus Pn times this e to the phase factor altogether will be some phase, be plus or minus 1, because remember we are talking about Z4. So G square should be plus or minus 1. It turns out, and I won't describe this, why that is the case, the natural choice is Fpn, F minus Pn is equal to e to the power of 2 pi I Pn square. And this actually follows from the discussion of the Higgs branch and the Coulomb branch. Because in the Higgs branch, the way I had defined the Higgs branch, what happens is that on the root lattice of SU2, it acts as a +1. G square acts as a +1, whereas in the fundamental conjugacy class of SU2, it acts as -1. Okay. And that's exactly the condition given here. Now, one loop modular invariance. This requires a lot of the string technology. So I will just state the result here. So what happens is that in string theory, maybe I just mention. Can I use the blackboard? Okay. So if I look at the string worldsheet, at one loop level, that's torus, right? That's a T2, and it will have 2 cycles. So one of them, let me call it sigma direction of the string, the spatial direction of string, 2-dimensional, and T is the time direction, the worldsheet time, okay? And this is the torus, so these are both have cycles. So if I want to write down the partition function, so now we want to write down the partition function for G invariant states, right? G is this orbifold group element, G. So G invariant states, well, then that's nothing else but the trace over the Hilbert space of the original string theory. And you have 1 over n divided by 1 plus G to the power of n minus 1, right? In our case, n is 4. Sorry, this n I shouldn't confuse. So let me just write explicitly just that. Okay. This n I should not confuse with that n lattice, Okay. So this is so I have to compute the trace of this times, of course, q to the power of L0, q bar to the L0 bar. This is the partition function. But insertions, in the usual theory, without doing any orbifolding, it would be simply identity here, and that would be the case, right? But now what we want to look at is the partition function of G invariant states, so I have to apply the projection operator, right? But at the level of string, at the level of this the path integral formulation, what this G means is that I look at the same diagram, sigma t here, except that here I twist by G. Okay. So as I go from, because the G action in the path integral language will, when you evolve along the time direction, it comes back here by twisting by G. No? So you get all these sectors here. So 1, 1, plus this, plus G square 1, etc. All of these sectors. Okay. So that is what gives the partition function of the G invariant states in the original Hilbert space. But now, if I just stop here, this will not be a consistent string theory, right? Because the string worldsheet has this SL2Z, PSL2Z modular group. So a particular element of this group is exchange of the 2 cycles. No? This means that in order to have modular invariance, I must include also a diagram like G1. No? This is a new Hilbert space. This was not there in the original string theory. So these are called the twisted Hilbert spaces. Twisted Hilbert spaces. Or twisted string Hilbert spaces. Okay. But then again, by Dan twists, you see this is not enough for modular invariance. You must also include GG, G to the n minus 1, G, right? You to get that. And this level matching condition that I'm talking about is the statement that when I do one more Dan twist, right, then which goes to G to the n, that better be the same as the first one. Because we are talking about an nth order, no? That gives a very non-trivial condition, which is called the level matching condition. So that condition is what I have written down here. Equation number 8 there, yeah? That is the condition. And furthermore, I should also point out that there are some peculiarities for the asymmetric orbifold. In this diagram, you see, when I did this is, by the way, it's called S transformation. When I go from here to here, there are some numbers which come, some numerical factors which come in the front. Okay? That numerical factor happens to be something like this expression which I have written down here, which is square root of determinant prime of 1 minus g divided by the order of I star over I. Okay? Now, in order for this theory to have any Hilbert space interpretation, that number better be an integer, right? Otherwise, it would make no sense. Now, one can show that, in fact, it's not a new condition. It is automatically satisfied if your original lattice was even and self-dual, if original gamma lattice was even and self-dual. So this is not a new condition, but I mean, it's not an extra condition. This is automatic. Furthermore, what is interesting is that if you look at the vertex operator algebra, okay, the vertex operators of the untwisted theory, no? The algebra of that, then the dimension of the irreducible representation is precisely given by that number, the square root factor. Okay. So which tells you that these twisted sectors, under the action of the vertex operators, they transform into another, and is a irreducible representation. It's an integer, yeah. This is an integer, yeah. Yeah. You see, it was, in fact, that was initially the kind of, many people were not even looking at the asymmetric orbifold because they saw that there was a square root appearing. And there was no way to, I mean, how can it be? How can it make sense, no? But then it was shown by various mathematicians, Conway and Lepofsky and so on and so forth, that this is, I mean, they obtained some results, and if you apply that to the self-dual lattices, then it's automatically true. Sorry, repeat. You take the positive square root. Yeah, yeah, yeah. It's a positive square root. Yeah. Right. Yeah. No, sorry. No, what did I do here? No, this I did already. Yeah. So the next one here. Okay. So this, the asymmetric orbifold details are all given in these two papers, 1988 and 91 papers. So what were the conclusions? By imposing level matching conditions and choosing different values of R, we were able to get all the Nikulin points in that original table that I showed in the second page, except for these 2 points, RA delta equal to 1, 1, 1 and 2, 2, 1. Because in these cases, I is very small. The dimension of I is very small. It's just 1-dimensional or 2-dimensional. And there was not enough space to put this shift vector V. This was coming from the level matching condition, right? This level matching condition, yeah, that equation number 8, that tells you that V was a shift that you have to put inside the in the invariant directions. And it depends on the S, or in other words, R. It depends on the R. For S equal to 1 and 2, R equal to 1 and 2, V square is not equal to 0. So you have to put the V somewhere, okay? And there is simply not enough space to put that, no? So it's a matter of the lack of space there. But this could be remedied by, if you compactify on one more spectator circle, no? There's sufficient space to put these shift vectors. The only thing is that in 7 dimension, we cannot get those models. In 6 dimension, we can get those models. Now, this is the important point that I want to emphasize, that all the remaining points can be connected to each other by the mechanism I mentioned, going from Higgs branch to Coulomb branch from the field theory language. I first described that. But okay, so this is, yeah. So on the M theory side, these transitions will be non-perturbative, right? Because these are topologically distinct Nikulin spaces, right? So that's very difficult to study in the M theory side, but in the heterotic side, it's perturbatively realizable, no? Another point to mention is that most of the Nikulin points do not admit spin structures, okay? So what does it mean? So remember, what is M theory? M theory is a theory of membranes, right? The low energy effective field theory of M theory in 11 dimension is 11 dimensional supergravity theory, right? And then on top of it, we have membranes. No? That is the M theory. Not much has been understood because membrane theories are very, very difficult to quantize. So I don't think, I mean, that's still open issue here. So we cannot do much with the M theory at this stage. Only thing we know is the effective field theory is 11 dimensional supergravity, plus membranes. So what this is saying is that, so you see that from the fact that there is no spin structure, that tells you that if I start from the 11 dimensional supergravity fields, the massless supergravity fields, and you do a Kaluza-Klein reduction on this Nikulin space, there will be no fermions, right? Because there's no fermion spin structure is not there. So therefore, all the Kaluza-Klein modes will be bosons. Okay. On the other hand, in heterotic constructions that we are finding, there are fermions also. It's not just the bosons, but fermions also. But one can prove on the heterotic side that the fermions appear only for charged states. There are no neutral states, no neutral fermion states. So therefore, there is not a serious contradiction between the M theory, because what that says is that on the M theory side, fermions must come from the membranes wrapped on various 2 cycles of the K3, of this Nikulin space. That's not because membranes are localized. It doesn't see the full Nikulin space, the 4-dimensional space, right? It's some localized around some 2 cycle. So that can admit spin structure. But again, the details we cannot work out unless we make some progress on the M theory side, membrane theory, studying with membrane theory. Finally, one comment, I mean, all of this discussion, there's a little, it should be taken with a grain of salt, because these theories these are not supersymmetric, so they all have tachyons. Okay, it is true that we can, the large part of the moduli space, the tachyons are massive, so you can ignore them. Okay, in that case, all these discussions go through. Right? However, we have also seen in one of our previous papers that even though you may start from the region where there is a tachyon is positive mass, there is a quantum effective potential is generated, and it's no longer flat direction. There is a potential which drives you to the region where tachyons appear. So this is a kind of a question mark there. Okay. Yeah, I think that's all. I will just stop here. Right. Yeah. Yeah. Okay. I think the lunch time.